label it as 1. Then ask yourself, how many forces acting on this charge? You have two other charges here. This one will push it, right? Okay, this one push it, got 1 force from number 2, right? How about this one? Is number 3 pushing this?
Yeah.
Oh yes, they are all positive repel. Therefore, you got another force here, which is number 3. Therefore, the force on number 1 will equal to F2 plus F3, right?
Yeah.
That's it. And do you have to consider direction?
Yeah.
Of course, but this one is so easy. You can forget about the direction. Just calculate F1. It equals F2 plus F3. You can remove the 3 arrow cap here. Do magnitude calculation directly. Because they have the same direction, right? You just add the 2 magnitude together. That's it. And what's the direction? It goes to the left. The job is done. Therefore, for this problem, you just concentrate on the magnitude and ignore the direction because it's too simple. And this is for number 1. For number 2, you put it down somewhere else also. Then ask yourself, how many forces acting on this guy?
2.
On 2, okay. Number 1 will push it which way? To the right. Okay, this is the force from number 1. And how about number 3 on 2? Okay, to this direction. This is F3. And if you look at this picture, are they equal in magnitude?
Yeah.
Yes, because they are all identical, right? Therefore, this push and this push, they are equal, but opposite in direction. Therefore, the so-called F2 must equal to F1 plus F3, right? But they are opposite in direction, therefore they cancel. You got 0 directly. You don't even need to calculate. And the solution is obvious. And that's number 2. For number 3, okay, then will number 1 push it? Oh yes, to the right. And will number 2 push it? Of course, push it. The same direction. Therefore, the force on number 3 it equals F1 plus F2. You see? And the question is F1 here equals F2?
No.
No, why not?
Equal. Because of the R.
Oh, yes, the R is different. Now, this force must be very small compared with this one. Why? Because the distance is doubled. For the equation, you have something over R squared. If R is doubled, look at the solution. What's the solution? It's 1/4, right? So the force is just a quarter of that force. Okay? But only at the middle for this one, they are equal and the opposite in direction, then no force basically. This is very easy. And you can do it in vector or do it in scalar form, just calculate magnitude. Either way is fine. Okay?
So what do you do after? So what do you do after you find all your forces to get the answer of net? The net
Okay,
force?
I can show you that too. The idea is it's simple. All right, let's do it formally. For number 1, okay? For number 1 charge, the force F1 will equal to F2 plus F3. Then F2 is the force from number 2 charge. Therefore, it equals K times Q1, Q2 over 0.2 squared plus, this is I, of course, negative. And the other one, F3, also negative, K times Q1, Q3 divided by not 0.2, this time it's 0.4, right? Also I. then you got it. You have negative k common factor and q1 common factor, right? Then inside you will have q2 divided by 0.2 square plus q3 divided by 0.3 square, then times I. That's your solution.
Why does the k go negative?
K not going negative. Because you have a picture here.
F4.
You said this is the x direction,
oh,
right?
yeah,
This is
sorry.
the positive, therefore backward all negative. Both of two forces, they go backward. Therefore, both are negative. Okay? But here, you don't have to put negative sign here because it's a vector. Here, if you ignore the negative sign, it's going to be wrong, right? Because to the right is positive. I think you should stop here. You don't have to calculate even a little bit further. No, just stop here. And Q1, Q2, Q3, they are all given. There's no reason you put in all the numbers to calculate. No, we don't have to do that. Okay? Of course, if you are an engineer, you need to do that. Without number, you cannot design your product. Okay? So, but you are not
I'm not an engineer.
engineer right now. You are a physicist. You just do your physicist job. Stop right here. Because following things are so easy. Everybody can do it. Okay, let's see number 2. Number 2 force, which is F2, it equals F1 plus F3, right? And look at the picture here. F1 is positive, F3 is negative, right? So F1 equals what? Equals K times Q1, Q2 over 0.2 squared times I. That's F1, positive. F3 goes to the left. It's negative. Therefore, minus K times Q3 times Q2 divided by 0.2 squared times I. Then you combine them together. 0. Why 0? See, denominators are the same. The K, they are the same. Q1 and Q3, they are equal, right? 3 identical charges. Therefore, this numerator, the same. In other words, the first term is positive, second term is negative. They are the same thing, therefore 0. Okay? That's the second force. If you try to calculate this one, this is the force on number 3. It will equal to F1 plus F2, the same thing as this one. And F1, F2 both goes to the positive direction, therefore both positive. Therefore Q1, Q3, 0.4 squared times I, then plus K times Q2, Q3, 0.2 squared times I. Therefore, you just take the common factor out. You have Q1 divided by 0.4 squared plus Q2 divided by 0.2 squared, then times I. And the job is done. And you see this one and this one, they are exactly the same in magnitude. The only difference is this is positive, this is negative. The other parts are exactly the same, no difference at all. Oh, you said, no, they are different. Here is Q1, Q2, here is Q2, Q3. But they are identical, the same, no difference. Okay? The best way to do it is that because the 3 charges are identical, you don't have to leave this one and this one here. All going out, you just put down square. here becomes water. And that's more beautiful, huh? And this one, the same thing, just square this. This one is 1, this one is 1. And can you do it over here? Over here? No, you don't have to.
It's
Because it's 0. 0 is better than anything.